Okay, welcome back to the third and final video where we're looking at work, energy, and power. In this one, I'm just going to unpack the concepts of power a little bit more, and then I'll put it all together with the definitions of energy and the various types of energies that we typically find. So, power is defined as the rate at which work is done, right? So, rate at which work is done. So there must be some kind of link to the definition of work. So power is equal to work and the time rate of change during which that work is completed. So we learned in the previous video that work is defined as force times distance, and there were various scenarios to which we applied that. We applied it to treadmills, we applied it to bicycles, we applied it to a box sitting on a surface, and I'm applying a force to it, and then the object tends to move in the direction of force application. And we looked at how much work is done depending on the distance over which I tend to apply that force on this particular object, or the distance that that object tends to move. We defined the fact that work can be positive, negative, or equal to 0. It can happen horizontally, but work can also be done vertically, as we did in the case of the treadmill. So if I apply a force upwards and the body tends to move upwards, then the force and direction of movement are in the same direction, and therefore I'm doing positive work on this particular object. What can also happen is I apply force upwards, but motion is happening downwards. Say, for example, if I was doing a pull-up. So in a pull-up, I might be in the top position. I'm still applying a force upwards, but my body is being lowered down through eccentric contractions. Therefore, I'm doing negative work. So the key with all of this was the fact that I also had to factor in the direction in terms of the difference or the angle between force application and the direction of motion. Okay, so that was the concept of work. So if I substitute that definition in for work, it's just the force times distance over time, and therefore we can tell that the units of measurement for power, if I look at, well, what is the unit of measurement? It is the units of work over the units of time, or in other words, the units of force times the units of distance divided by the units of time. So again, that's going to be Newton meters. In terms of distance is measured in meters, and force is measured in newtons, and time is measured in seconds. So that's Newton meters per second. But remember, Newton meters we also defined as a joule, so that is equivalent to joules per second, and that has a specific name called a watt. So W-A-T-T. Right, it's the same unit of energy that, for example, light bulbs are measured in, or electricity in general. That's another form of energy. So how much wattage can you produce in a given period of time, right? It's an equivalent to how much force you produce over a given distance per unit of time, joules per second. Something can also strike you here, meters per second. What is that typically representative of? And something that should jump to mind is velocity, right? So what you notice is if we restructure this slightly, force multiplied by distance over time, I could rephrase this as force times velocity. That's also a measure of power. How much force am I producing at a given velocity? So again, that's also measured in watts, and you can tell it's got the same units of measure. It's still Newton meters per second, right? So it's still measured in watts. So the key concept here is doing work more quickly results in greater power, right? equals increased power. So if I decrease the time in which I complete a given amount of work, the power tends to increase. Or if I produce more force over a given distance, or I produce a given force over a greater distance, all of those will tend to increase the power. Same thing in terms of the force-velocity relationship. So how do I increase power? I can increase the force that I produce, or I can increase the velocity with which I produce that force. So if you think about this, is very applicable to cycling. Like the faster I need to cycle, the more power I will tend to generate, right? Or the more force I produce, the more power I tend to generate. If I apply it to these same examples here of moving a particular object, so say for example you have a person lifting 100 kilograms. Actually, we've got two people, right? So we've got two scenarios that we want to unpack here. In both scenarios, we have a person lifting 100 kilograms. The person is lifting the 100 kilograms a distance of 0.5 meters. Right, so maybe this person is doing a deadlift, and from the bottom of the deadlift, so if this was your person over here, and he's trying to lift the bar with some weights on, and he moves it to a new position when he stands up, and that distance that he moved it was 0.5 meters. The work that that person is doing is going to be the same in both instances, right? So it's the force, or in this case the weight of the object, so 100 times 9.81 times the 0.5 meters, and that gives me 900 and sorry, I just want to half of 981. 981 divided by 2 is 490.5. So that's 490.5 joules. And like you said, that's going to be the same in both instances. 100 times 9.81 times 0.5. That's 490.5 joules. Okay, but there may be a difference in terms of how quickly one lifter lifts the weight compared to another one. Say lifter number one lifts this weight in half a second, 0.5 seconds, and say lifter number two takes twice as long, so it takes 1 second to lift that weight. So that's where power becomes a useful measure. Which of these athletes is the more powerful? So again, it's defined as work over time. So in this case, it's 490.5 divided by 2, which is going to give me 981 watts that person will generate in that period of time. In this case, I again also want to calculate how much power this person generates. That's 490.5 divided by the 1 second, which stays 490.5 watts. So clearly the person that could complete a given amount of work in a faster period of time, so this should be divided by 0.5, not 2. My mistake. That's half a second. Clearly the person that can complete a given amount of work in a faster period of time can generate more power, or is the more powerful person. So this same principle applies to training. So whenever you are in a gym environment and you are trying to train the rate at which you can develop force, the key there is always speed of movement. So that's what we can kind of derive from this particular equation. If I can generate a given amount of force, the speed of movement is always going to be key for sport-specific applications. So oftentimes what athletes will do in order to build power is to work at a sub-maximum load, so typically 30 to 50% of 1 rep max, but trying to move that resistance as fast as possible. And that helps with power generation. So speed of movement becomes really, really critical there. The last thing that I want to kind of finish off on is just the concepts of energy, right? So energy is something that we've been speaking about for quite a bit. So energy is defined, funnily enough, as the capacity to do work or to perform some action. Alright, so the key here is that it's also measured in joules. That's the standard of measure. And it can never be created nor destroyed. And that's the key part. It's merely transferred from one form to another. Right? So the fact that you can move your eyes at this very point in time as you're reading these sentences is due to the energy that your muscles have, right, in order to move those eyes. So the key energy generating molecule in your muscles is ATP, and that comes from the food that you eat, right? So say, for example, the chicken that you had earlier or sometime this week, or the beef, or the grains and vegetables, so on and so forth. And in the case of animals, remember, animals somewhere down the line eat plants, and the plants directly get their energy from the sun, right? And the sun gets its energy from nuclear reactions that happen, so on and so forth. So it's just an endless process. So in many ways, you are a 100% solar powered being, right? I mean, it's getting all your energy from solar energy in essence. But there's many forms of energy. So some of the ones that apply specifically to our field of study are your potential energy, which is in essence stored energy, right? And we have kinetic energy, which is energy due to motion. So these are all aspects that we've kind of mentioned in various respects already. So there's two primary potential energies. So one is gravitational potential energy, which is in essence energy relative to position on the earth, right? And is expressed as mgh, mass times gravitational acceleration times the height at which you are. So say, for example, that an object is resting on a table, the amount of potential energy it possesses is equal to its weight multiplied by the distance above the ground that it is, right? So I'll get to the link between this and kinetic energy a little bit later on. The other form of potential stored energy is strain energy. So in many respects, that's elastic energy. So if you think about an elastic band, a rubber band, even your muscles have stored energy within the elastic elements of it. And that is typically expressed as 1/2 kd squared, where the k component is the what's called the spring coefficient. In other words, if you think about a typical rubber band, they would have quite a low elastic coefficient over here, right? It's stretchy and it tends to return to its original form, but the amount of energy that it can store is actually very low. But think about the shocks on your car. They are very, very stiff, and they can therefore return quite a fair amount of energy. So in many respects, this refers to the stiffness of the spring, and d is the distance through which that spring is deformed. So in in essence, you could think of it as the deformation distance, how much you tend to stretch it, and what that coefficient of stretch is, or stiffness is, will tell you how much energy that spring can return. Then there's two types of kinetic energy. So what we have is linear kinetic energy. It's the one that you guys are probably most familiar with, which is just 1/2 mv squared, right? And the second is rotational kinetic energy, right? Energy possessed in a rotating body is equal to 1/2 times the moment of inertia times the angular velocity squared. So you can see these look very, very similar. We've already kind of spoken how this is derived. In many respects, you can just derive this from this equation by simply replacing the angular velocity component. Remember that linear velocity is angular velocity times radius. So if I can kind of replace that in there, I can derive this version of the kinetic energy equation. Alright, so in many respects, this is the main energy constituents that we deal with in the study of human motion and biomechanics. I guess there's one last thing that this would be coupled at. So the combination of kinetic energy plus potential energy gives us the mechanical energy of the system, right? So this over here is just the total mechanical energy of a system. So most systems will have some combination of kinetic and potential energy. Sometimes there might be no potential energy and it's just kinetic energy, but that's the summation of these two that gives us the total mechanical energy of a body or of a particular system. And I think that pretty much summarizes everything that I wanted to speak about in this brief basic overview and introduction into the concepts of work, energy, and power. I guess the main things that I want you guys to take away is just the link between what energy is and how it's defined, how work and energy are intricately interwoven, and the fact that power is just the rate of change of energy or of work in many respects. And also, at the end of the day, the theory is useful, but it's its application that's ultimately what we're interested in, right? So again, like I mentioned, every single time that you cycle or you run or you row or whatever it is that you do, you are generating power, you are completing a given amount of work in a given period of time, and those are all measurable variables that have significant implications in terms of human motion and things like efficiency and training modalities, etc., etc., etc. I think that's it for now, and I'll see you guys next time.